So our next speaker is Jim Eisenstein from California Institute of Technology.
Well, thanks the organizers for inviting me to give this talk. It's only 30 years of my career that I'm going to talk about today. Allan MacDonald and I have known one another for much more than 30 years, and my debt to him goes back long before the stuff I'm going to talk about today. When I heard about this event and was invited to come and give a talk, I, of course, obviously wanted to do it. I mean, I've known Allan a long time. We've had a great relationship. I've benefited enormously from him. But on the other hand, I've been retired for 7 years. I shut down my lab 4 years ago. I've spent my time since then doing woodworking, and I have not followed physics at all. So that put me in a bit of a pickle about what to do. So I thought the best thing would be to go back into my old talks and look, or into my, if you like, bibliography, and look for those things that, number one, I thought were really interesting, and number two, Allan helped me with. And it turned out it was everything. Well, at least the things that Allan helped me with, those were everything. Whether they were all interesting or not is a subjective question. So that's what I'm going to do today. I list my affiliations here as both Caltech and Bell Laboratories, the old Bell Laboratories where we had this funny bell symbol. This is because much of the work I'm going to tell you about today actually took place at Bell Labs, both in the late 80s and in the early 90s, probably before some of you were even out of diapers. And furthermore, it was amusing to me today to listen to the two talks already. I worked with this old stuff called gallium arsenide, and it was called the material of the future. And some people said, yes, and it always will be. So it's kind of out of fashion these days, but it was really cool. It just really was. And we could do lots of neat stuff. So that's what I'm going to tell you about today. I'm going to tell you about the fact that I had a lot of help from a friend of mine. That would, of course, be Allan. Back then, we had telephones. And I worked for the phone company. So we had a very fancy phone. It had push buttons on it. And I could pick that phone up. This is the amazing thing, is I could pick that phone up in my office and dial a number that corresponded to Allan, and he would pick up his phone in Indiana. His phone was not quite as good as ours, but the really amazing thing about this was he picked up the phone himself. That's not so much true anymore. And it was great. I could call him up on the phone and Allan would say, hello, and we would start a physics discussion. And it was immensely important to me and to the development of the work that I've done. So one of the experiments, as I said, I'm going to kind of pick out some that we worked on, this thing called Coulomb drag, which, by the way, the name of it was given by Steve Gervin. He may not remember this, but it was at an Aspen conference. I had developed this scheme, which seems passé today, for making electrical contacts to separate layers in semiconductors. And this is something which was hard to do, and we had to come up with a cute scheme. And so once I had the scheme for doing this, I wanted to come up with some experiments to do with it. And probably the most obvious thing that certainly came to my mind as being obvious, was to, well, drive a current through one two-dimensional electron gas layer and see what voltage develops in one that's parallel to it. It seems like a simple question and one that could be kind of fun. And I talked to actually Steve, as I mentioned, at Aspen way back, I think probably 1989 or 1990. And he said, yeah, that would be Coulomb drag. So there it is. So that's the experiment. It's as simple as can be. It's a transport measurement. It's what I've spent my whole career doing is basically, I like to tell my kids, all I ever did was measure Ohm's law. I measured a voltage, I divided by a current, and I got a resistance out. And I did that for 40 years. When you got something that works, you stick with it. So this is a really tiny effect. You could imagine doing it with a couple of sheets of tinfoil, but you'd be disappointed. The voltage that you would measure would be you'd probably measure a voltage, but it wouldn't be due to Coulomb drag. It would be some parasitic effect. So it's usually very, very weak. But if you think about it for a little while, if you measure this in this way, where the current is flowing in one layer and the voltage is being measured in the layer that doesn't carry any current, and you make an incredibly simple model of this, you realize that this is a transport measurement that actually tells you about momentum relaxation between the two layers. So normally you would think, and that momentum relaxation can occur via various processes. The impurity scattering that goes on in each of these layers doesn't count. And that was kind of miraculous and very interesting and allowed us to make a measurement of electron, it turns out in this case, electron-electron scattering between two layers without being bothered by the fact that there was impurity scattering going on all the time. So think about that for a little. It comes out very, very simply. And obviously, the thing you would normally guess, if it were just Coulomb scattering of electrons off of one another in the opposite layers, well, it probably scales as t squared, right? Because these are degenerate Fermi systems. That was the level that I could think about it anyway. So we did the experiment. Actually, a postdoc of mine, Tom Gramila, did this experiment in 1991. And sure enough, it looks kind of like t squared. There's this voltage, it goes to zero at zero temperature. So it's very different than the ordinary resistance of a metal, which saturates. This just goes on down to zero because the scattering rate goes away as you go down in temperature. But you can see that it's not really t squared. There's some things going on in there that maybe you don't understand. And so that's where Allan comes in. I couldn't make this calculation. I just stole this equation from some book and put it up here for you. I couldn't have made this calculation. Allan did it and found out that, yeah, I was right. It is t squared, which was good. But there was much more to it. Number one, he got a magnitude for it. And furthermore, he found out that how it depended on the spacing between the layers. It turns out it's very sensitive to the spacing. The reason, because there's a lot of screening going on. And in fact, the screening both within one layer and between the two layers is important. So that's fine. He made this nice calculation and we compared it to the experiment and it didn't work so great. Well, it worked pretty good. These are the calculations for different spacings between these two quantum wells, and they're on the same page. As one of my former postdocs would say, if it's on the same page, it's good enough. And it's not a log plot anyway. But they're flat. They're t squared. This is the scattering rate divided by temperature squared. So it would be flat if the naive model was correct. And it's not flat. It's got this big bump in it. And this bump is the same. You can see it's the same for all three separations between the layers. And that's because there's some other longer range thing going on. And that turns out to be phonon exchange between the two layers. And that is what the model then becomes. It's both Coulomb, direct Coulomb scattering, and then some kind of phonon-assisted process. We made later experiments with much lower electron densities and different layer spacing. You can get this phonon contribution to go away or become negligible. And so I'm not going to go into that. But anyway, in 1998, Allan and a postdoc of his worked out a nice model of this, and we think we pretty much understand the whole business. And now we come back to my freshman physics exam in 1971, which I'm still annoyed about. There was this problem on my freshman physics exam. There it is. Those are supposed to be layers, sheets in cross section. And it's a 3-sheet capacitor from my physics final exam. And the question was, how much electric field is in here, in between those two sheets that are short-circuited together? And of course, needless to say, I got it wrong. I said there was some electric field in there. Little did I know that, in fact, I had gotten it right. And I've applied, actually, but it turned out the statute of limitations is over. I couldn't get my grade changed on the exam when this thing figured out. It turns out that, in fact, there is an electric, these are the two quantum wells that contain these two-dimensional electron gases. There is a little electric field in here when the gate voltage is applied. Mostly the electric field's out here, but a little bit of it pinches through. And the reason is because the density of states of a two-dimensional electron gas is incredibly small compared to that of a normal metal, like a piece of aluminum foil. So there's a very little electric field there, but there is some. And you can do these tricks of making electrical contacts to the different layers to make a measurement of that. Now, and that measurement, as it turns out, the value of this penetrating electric field is given by, essentially, the inverse compressibility of the electron gas nearest to the gate. So this simple measurement that was on my physics exam in 1971 actually tells you how to measure the compressibility or the density of states, if you want to call it that, of a two-dimensional electron system. So I didn't know how to make these calculations at first, although I did steal a computer program from Greg Bobinger, who's also in the audience, for doing self-consistent calculations of the subband structure in these things. And if you do these calculations, you presumably can determine what simple theories would predict for this value of E sub p, the penetrating field. Allan helped me a lot with this. He had a student, Jun Hu, who gave me some results of calculations for specific examples that I could then figure out how to replicate and go through a complete analysis of this problem. It's one of the few cases in which I wrote a long PRB with lots of details in it. Here's the result of those calculations. This is another way, this thing called D is really just this penetrating electric field or this compressibility. And you find out, the first fascinating thing you find out is it's negative at low densities. The compressibility is negative, which sounds horrifying, but it's true. The electron gas has a strong electron interaction, exchange interaction that drives it negative at low densities. And we could measure that. You can see the fuzzy curve that shows the noise on it. It goes very strongly negative, and then somehow disorder comes in and it pops up positive again. These are calculations which I did following the ideas and the tips I got from Allan and his student. A very simple-minded, both local density approximation and just simple Hartree-Fock calculations of what that penetrating electric field ought to be. So this measurement gave a beautiful illustration of a very simple piece of physics. You can also use this kind of measurement to look at other, perhaps more interesting things. And in particular, we looked at the fractional quantized Hall effect, where we could measure the compressibility. I mean, after all, you all learned that fractional quantum Hall state is an incompressible quantum fluid. So you might want to measure the compressibility, which we did. And we found out, this is, by the way, the inverse of the compressibility, that around the 1/3 state, sure enough, the compressibility becomes very, very small. And you can turn this measurement around and actually use it as a way to determine the chemical potential jump that occurs at various fractional quantum Hall states. This then is actually a thermodynamic measurement of the energy gap of a quantum Hall state, different than what you normally would do by measuring, say, resistivity versus temperature. So that was a fun thing to do. Again, Allan had a big impact on my understanding of that. Okay, let me turn to the third topic. Third topic is tunneling. We just heard something about that with these Moiré systems, which I found fascinating, that now the same type of measurements that we did with such great difficulty in bilayer two-dimensional electron systems in gallium arsenide are now being done in these stacked Moiré systems with some kind of tunnel barrier in between. Well, we did this a long time ago. This is about 1990, this data here. And we measured just exactly what I said, the tunneling conductance between two-dimensional electron gases, because we had these separate contexts we could put on the different layers. And those systems are very clean. And it turns out that, as you might guess, momentum perpendicular to the page here is conserved. And because of that, the tunnel spectrum is extremely sharply resonant. Right? It's not like tunneling between two 3D metals. They're not 3D, they're 2D. And because of that, combined with good momentum conservation, you get a very sharp peak at say, at zero bias if the densities of the two electron gases are the same. So that's cool. That's really neat. Did a lot of that. This is data from Sheena Murphy, 1995. She was a postdoc of mine. And we measured the temperature dependence of this line shape. And of course, being stupid, I just said, well, it's going to be t-squared again. For absolutely, it turns out it is t-squared, but for totally the wrong reason. It's not Fermi surface smearing at all. Fermi surface smearing has no effect on this. If you have momentum conservation, this resonance will be sharp at all temperatures. But in fact, it's not. As you measure it, when you measure it, it is in fact broadening as you get warmer and warmer. Allan was visiting Bell Labs at this time. And I went into his office and he looked at the data and he said, it's an interaction effect. And we thought about that and we worked on it. And in fact, it's true. We elaborated on this to a great degree. What's going on here is that the thing that limits this line width, this tunnel resonance width, is actually the lifetime of the momentum states that you just said were conserved. That lifetime can be limited by various things, but in the temperature range of these experiments, it's predominantly limited by electron-electron scattering. So one can make a calculation. It was done in the early 1980s, even before that, I think, for how what is the lifetime of a fermion near the Fermi surface as a function of temperature. It goes as t squared. This is not Fermi. It's not the t squared that I naively thought it might be, but it is t squared. This is the lifetime of a quasi-particle above the Fermi sea. Goes back a long time. And we measured it and looked at the temperature dependence and found out it scaled pretty much as t squared. By the way, you can see, did I put it on? Yeah, there's a logarithm in there. We never could detect the logarithm. We're not that good. Pretty much t squared for all various densities, normalized by the Fermi energy the way that it should be. Problem was that those theories from 1982 weren't right. And it turns out that they were not right for both a silly reason, they made numerical mistakes, and also for a more subtle reason that there are higher order many-body contributions to this lifetime that need to be considered. And this became an interesting problem. Thomas Jungwirth was also a postdoc of Allan in the mid-90s, looked back at this problem and found that early theories had ignored this factor of pi squared over 2. Okay, fine, that's a silly mistake. But also this interaction business, that this factor W, which can be substantial in these two-dimensional electron systems if the density is sufficiently low. So these calculations were made by Thomas and Allan, as well as by Lian Zhang and Shankar, who's sitting here in the audience. And they found out they were able to find very good agreement between what we measured for this line width and what they were calculating. Okay. Now, I don't know how much time I've already been talking, but the thing I've talked most with Allan is this problem of strongly correlated two-dimensional electron system, bilayer two-dimensional electron systems. And in particular, there are many examples of that, but in particular, what happens when you have two layers, identical layers for simplicity, that are each at 1/2 filling of the lowest lambda level. In however you want to describe that particular configuration. If you bring them close together, what happens? And in experiments that were done at Bell with Greg and with Sheena Murphy a little bit later, we found out that interesting quantum Hall states appeared that you wouldn't have expected to see if you thought about the two layers independently. For example, at filling factor 1/2 of an individual layer, you have a compressible state. There's no Hall plateau in gallium arsenide anyway. When you bring them close together, the filling factor is now unity, it's 1/2 + 1/2, but a quantum Hall plateau shows up. And you can wonder about what that is due to. There's also one at 1/4 + 1/4, which unfortunately I don't have time to talk about. It turned out to be, I mean, it's very interesting, but less interesting than this one. So, and I think Greg may come back to this a little bit in his talk later. It turns out that we can make, well, not we, Lauren Pfeiffer can grow a lot of samples with all varying thicknesses of the barrier and this, that, and densities, all various things. And so we can construct a kind of quasi-phase diagram of samples, red ones and blue ones. Red ones that show a quantized Hall effect at this 1/2 + 1/2 state, and blue ones that don't, as a function of the separation between the layers and the strength of tunneling. And we found, as Allan predicted in 1990, that this phase diagram, you might have guessed that there would be a regime at strong tunneling where there would be a quantized Hall state. That's sort of a simple picture. But as the layers got, as the tunneling got reduced to become very, very tiny, you would think that mechanism would go away. But in fact, it persists. There is still some regime of this phase diagram where there is a quantized Hall state, even in the limit of very little tunneling. That's what I'm going to talk about for the rest of the time that I have. So really that orange line on the vertical axis there. Here's just as an example, sort of a proof that what I'm saying is not completely baloney. This is a sample, this is data from a sample in which the tunneling strength is 10 million times weaker than the mean Coulomb interaction between the particles. So this is really on that vertical orange line that I showed you. And yet there you have it. There's the quantized Hall state with a nice, strong, robust energy gap, much bigger than the tunnels, orders of magnitude bigger than the tunnel splitting. Now we go to Caltech, where I moved in 1996. And I had a very smart student, very capable student, Ian Spielman, who bonus problem that I gave him was go measure tunneling between two layers of electrons at filling factor 1. And he set up to do that. We had the separate contacts. We knew sort of how to do it. The most important thing was that Lauren knew how to grew samples now that for which we could make those contacts, and we were in the right regime that this thing might show up. That was highly non-trivial for him to do. And Ian happened on to one of the most spectacular results that I've seen in my laboratory. I'm not making any bigger statement than that, but in my lab, this, you know, the old phrase, they knocked your socks off. I mean, it really knocked my socks off. These are two tunneling spectra from the same sample. They are I versus V. The blue one, again, is for a sample where it's this, again, it's the same sample. The density is adjusted so that you're slightly too large. The separation is slightly too large to have this quantized Hall state. And there you see a tunnel spectrum which shows very little tunneling, exponentially small tunneling current at low voltages. This is a very interesting piece of physics itself, but I'm not going to talk about it. What I'm going to talk about is that you take that same sample and adjust the densities just a little bit, and that you get the red curve. And if that doesn't knock your socks off, I guess you're not wearing socks. I mean, this just blew my mind. And this is actually not, I mean, truth be told, this is not Ian's original data, but it's a refined version showing what looks to be a DC Josephson effect. It's not a Josephson effect, but it kind of looks like one. So that was one really neat thing. The next thing, I had another student, this was now Mindy Kellogg, who was working alongside Ian. I said, go measure Coulomb drag in this regime where the layers are close enough together that this exotic state turns up. And she went and did that. And I said, oh, and by the way, measure it in the Hall direction. In other words, do a Hall measurement on the layer that's not carrying any current. It's a drag measurement. It's current in one layer, there's voltages in the other, but it's transverse to the direction of the current. Normally you would expect there's not going to be any voltage there. There's no Lorentz force because there's no velocity on the particles in that layer. Well, so she set out to do this, to measure both the longitudinal and the Hall component of the drag. And lo and behold, and by the way, this was predicted. I can't say that it wasn't. Lo and behold, the Hall drag not only wasn't zero, it rose up and became quantized at exactly h over e squared. And since we're talking about funny referee comments, this one, the referee said we were violating the isotropy of space. I don't know what the hell he meant by that. I never figured that out. But that's what he said. All right. So those kind of suggested this is a pretty interesting state. Whatever this is, it's got some cool properties. There is this model. There's various models. I'm very sorry that I missed Shankar's talk yesterday. I was in the grips of the airline industry. There's various pictures you can use to describe this quantized Hall state at filling factor 1. One of which is to think of it as an exciton condensate. You have these two half-filled layers. You can make a particle-hole transformation on one of them and talk about electrons and holes. They can bind together, make a BCS-like wave function, only it's a BCS state of excitons, interlayer excitons. Those excitons can move. And if they do, they don't carry any current because they're neutral, but they can move. Okay. From an experimentalist perspective, the thing you want to do to get a hold of the excitons is not to put a voltage across the whole sample and measure like you normally do. You want to try to drive currents in opposite directions because these two, if you move an exciton from left to right, you have a current in one layer going one way and a current in the other layer going the other way. So you do this measurement and you might see something cool. And we did the measurement and we saw something cool. Here's again a cartoon of what the experiment is. This is Mindy's data. And again, it's the blue sample versus the red sample. But I apologize, the colors are reversed here. So if anybody's confused about that, the red one is the one that's below the phase point, the phase transition, or the transition, and the blue one is above. And this is the Hall effect. The Hall effect, everybody knows, goes up linearly with magnetic field, occasionally punctuated by plateaus that people get Nobel Prizes for, right? And that's what the blue data shows, right? Nice Hall data. But if you bring the sample down just below this critical point, you find that that's not true anymore. Now the Hall resistance just goes to 0. You're at very high magnetic field, and there's no Hall resistance. Again, take off your socks. That's pretty amazing. I mean, seriously, we're all jaded now, right? But think about it. It's really amazing. So these excitons are charge neutral objects. The idea was then that they're moving along in carrying this counterflow. It all sounds like a great story. Yahoo. Let's go crazy with this picture. Problem is, at least at the conceptual level, is you have a quantized Hall state here, and you're making contacts out at the outside edge, and there are all these edge states that you have to think about. And I don't understand them, and I was always kind of worried that maybe they had something to do with this measurement, and were not, so that our simple interpretation maybe wasn't quite right. So then came the lunch. We were at the Würzburg High Magnetic Field Conference. Allan, you remember this lunch? It went on for hours, at least 3 hours. I was there, Allan was there, Adi Stern was there. Adi and I were not believing what Allan was saying at the time. It went on for a long time. But nonetheless, he really, in the end, drove us in the right direction. That what we wanted to do was find experiments where we could claim without any ambiguity that we were observing transport through the bulk of this topological insulator, which has edge states on the outside. That's what came out of that conversation, at least to me. So we wanted to make Corbino measurements. There's a picture of a Corbino device, multiply connected. There's a hole in the middle. And others, including Klaus von Klitzing's group in Stuttgart, started these measurements actually before we did. We got around to them with a grad student of mine, Aaron Fink, and a subsequent grad student, Debalina Nandi. So there was this nice theory paper by Young Su, who's here in the audience, and Allan in 2008, related to this. What kind of ways, what could you do to generate these counterflowing currents? And there were two main scenarios. One was to make a circuit like this. Again, understand that these two pictures are layers, and on the left you have the inside of the or say the outside of the donut, and on the right you have the inside of the donut. So the region between is actually the bulk of the 2D electron gas. There is no edge state connecting the inside to the outside. So these were two ways, two circuits that you might wire up. They were so simple that I could understand them. We could put batteries on and resistors and measure stuff. And if you did this, especially in this what's called the drag counterflow, you have no physical connection between these layers. And yet you can have a current, let's say, flowing from left to right in the top layer, and a current flowing from right to left in the bottom layer, mediated by these excitons going across the bulk. But remember, we could also simultaneously measure ordinary transport through the bulk, not counterflow. And that has essentially no conductivity. It's a quantum Hall state after all. So there is no current. If you try to drive the currents in the same direction, it doesn't go. But if you try to drive them in opposite directions, counterflow, as we heard about in previous talk, it goes like crazy, right? That's the essential thing about this state. All right, and I see that I'm about to get scolded. So we did this measurement, and or I should say Debalina did this, and we found that these two currents, there are, I put a minus sign in front of one of them, so they come out to be on the same direction on the graph here. At low values of voltage, they in fact are essentially precisely equal, even though the bulk of the system is not carrying any current. As you go to higher values of the drive voltage, the bulk starts to carry current, and then this picture breaks down. And you have to include that if you want to understand the behavior at higher voltages. But fundamentally, it worked. I have another minute. Everybody else got more minutes. The last thing I want to say to you is something that is not ancient history. It's only nearly ancient history. This is about 5 years old. This was done after I had retired and I was trying to be a graduate student again. Actually a postdoc. I was trying to be a postdoc. I went and measured some more things. And here's just another illustration to show you, this is this tunneling business that I told you, this Josephson jump. As you come down in layer separation, it takes off like a rocket at a certain critical point. The Hall drag takes off like a rocket and becomes quantized at more or less the same point in the same sample. So the question is, can you learn anything else from these measurements? And in particular, what I got very interested in is what happens when you're above the phase transition and you don't see the Josephson current anymore. Can you detect anything interesting? And it turns out, a surprise to me, you can. So here's this, the generic response when you're not in the excitonic phase. There's this strong suppression of tunneling on low energy. If you look at the value of kind of, just define it in some way, the value of that gap and measure it as a function of, again, the layer separation, a simple picture would make it be a straight line, just dependent upon the density of the individual layers. Just take my word for it. We could talk about it more if you want later. And the fact is it doesn't behave that way. It comes down linearly, rather beautifully for a while, and then starts to deviate off and crash. Very, very strongly crash, right at the point where the supercurrent the Josephson-like current turns on. But well above it is it deviating from this straight line behavior. So that tells you that there's some remnant behavior of this anticipatory behavior of the excitonic phase well above the transition. And that's, I think, my last view graph. These are I believe, are pairing fluctuations in the system. I wish I'd been here, as I said already, for Shankar's talk. There's some evidence then that there is correlations occurring ahead of the actual onset of the more exotic behavior like the tunneling supercurrent. And with that, I will say thank you, Allan. It was a blast.
Okay, we're behind of time, but still we have 1 minute or two for questions from the audience or comments.
It's all old stuff. You don't have to ask any questions if you don't want. Oh, no.
Do you believe that those experiments show that this is a continuous phase transition?
Kind of smells that way, doesn't it?
Sure looks like it.
And I should point out that I kind of lied a minute ago. I said that we didn't know this ahead of it. There was no evidence of this ahead of time. It turned out, and this was a referee, and I think he's in the room. I'm not sure, but I think he's in the room. We had a lot of trouble getting that. I'm looking at you, Shami. We had a lot of trouble getting this one published. And I thought it was so cool. There was this from long, long ago. This is, I forget, this was Mindy's data from like 2002, maybe 2003. This is ordinary Coulomb drag. And this is, as a function, this is filling factor 1 of a single layer, and then going into the half-filled state of a single layer. And lo and behold, there was this stupid bump there, right at filling factor 1 for the total system. And we showed experimentally that it was there and that it went away if you went, this is a D over L of 2.6, which is way above the phase transition. So it was there. Allan, perhaps you can explain this. So I think the answer to your question is yes. I do think that it looks like a continuous transition.
Okay, so yeah,
My homework.
Yes, your homework. It's a bonus question.
all right. I think we should try to move on. The organizer told us that the next session will start 10 minutes later at 11:10. And please, those speakers of the next session come earlier to test your devices. And let us give thanks to Jim and all the speakers of the session.